So this talk is based on joint works with my former colleagues at CMU, Ahmad Abdi and Gerard Cornuders. So this talk, the outline of this talk is basically the following. So I'm gonna define the set covering problem and ideal clutters, and I'll define two important notions in clutter theory that are clutter minors and blockers. Okay, and then I will define some classes of clutters that are deltas, extended autos, and their blockers. And you show that I'll show that these are non-ideal clutters. Okay. The general motivation of this research is coming from integer linear programming. Okay, so integer linear programming is an optimization problem of the following form. So we want to find an integer vector satisfying this linear system of inequalities. Among the solutions, I want to pick the one minimizing this linear objective. Okay. So the first thing you can try to solve this be to relax this integrality condition. Then you obtain this linear program. As this is a continuous optimization problem, you can solve it in polynomial-time, but this pointer doesn't work currently. Oh. Okay. Maybe I should direct this. Okay. So once you relax this integrality condition, you get something called relaxation, meaning that the optimum value of this is as small as the optimum value of this integer program. So if you get integer solution to this relaxation, there will be automatically a solution to this problem. Okay, because IP is NP hard, if you get an integer optimal solution from this LP, that's a good situation. So you don't have to worry about solving integer programs in general. Okay. So that's the question. Basically, when is it that this linear program returns an integer optimal solution for every linear objective C? Okay. I say that a polyhedron is integral if all its extreme points are integer lattice vectors. So basically, a polyhedron is a convex set defined by a finite list of linear inequalities. Because a linear inequality defines a half space or hyperplane, it just looks like a polygon in two-dimensional space. And an extreme point R is just a vertex of this polygon. And I say a polyhedron is integral if all its extreme points are integer lattice vectors. Okay? And this question basically boils down to asking when the polyhedron defined by this linear inequalities is integral. Okay? So again, this linear program has an integer optimal solution for all linear objective if it's integral, if the polyhedron is integral. Okay. So, so when is it that this polyhedron integral? That's the question. But as I explained here, this question is a totally geometric question. Okay. And as you might expect, this is actually co-NP complete to test whether a polyhedron is integral. Okay. So I can ask you a simpler question after imposing some conditions on the constraint matrix. So I now assume that the constraint matrix is 0, 1, and the right-hand sides are 1, all ones. Okay. And then you can because a 0, 1 matrix has some combinatorial meanings, I can also use the combinatorial structures of this matrix system, as well as the geometry of this polyhedron. What I meant by that is the following. So you can label the columns of this zero matrix from 1 through n. Then each row corresponds to a subset of this index set n. Okay. Now you can collect the sets coming from the rows of this matrix. Okay. For instance, you have this 3-row matrix. The first row corresponds to set 1, 2, 3. Now you can construct the family of these 3 sets. Okay. Again, I'm interested in the integrality of this linear system. You can always take out redundant inequality. By redundant, I mean even after taking out that inequality, you still get the same solution set. Okay. On inequality being redundant is equivalent to say that the corresponding set is not minimal. So you can always keep the minimal sets coming from this family. Okay. Let me formalize that. So let E be a finite set of elements, okay, with some weight. And you take a family of subsets called members, okay, and I call this family a clutter if no member contains another, meaning this, every subset is minimal. I define covers. So a subset B of the element set E is a cover if it intersects every subset in the family. Okay, this is sometimes called heating set in the computer science community. And the weight of this cover is just defined as the weight sum of the elements. Okay. And the set covering problem, also known as the heating set problem, is the problem of finding a minimum weight cover of this clutter. Okay. Again, in this example, if you pick this element and this element, then this set will intersect all 3 subsets in this family. So this set 1, 2, 5 is a cover. Okay. So basically, if you give me like this matrix system, this inequality system, that will provide a natural integer programming formulation for the set covering problem. In this situation, if you look at this inequality, okay, this just guarantees that you have to pick at least one element from this set, so that this set can be covered. Okay, and then among the ones, you want to find something that's minimizing this linear objective. You want to find a minimum weight cover. I didn't explicitly said that these are binary, but as long as W are non-negative, optimal solutions should be binary. Okay. So and the 0-1 solutions will correspond to the covers of this clutter. Okay. Any questions so far? Okay.
You said that optimum solution is binary, but
there could be some non-binary solutions especially when W are 0. Right. Yeah. And if you assume like all W's are positive, then every particular solution should be binary. Because if you have some like non-zero that's greater than 1, then you can reduce it to 1 if it's positive.
Like if I have only one constraint, like x1, some of the variables then is 1.
Yeah.
And I might have a fractional optimum solution. So we are on IRP. Oh yeah. Oh, is that? Oh, you're saying.
Yeah, this is an integer solution. Yeah, if you only look at integer solutions.
Right.
Okay. Yeah, if you have any questions during the talk, just please interrupt me so that I can answer them. Okay, so given a clutter C, you can look at the incident matrix of that clutter. Basically, that matrix whose columns are labeled by the element, and the rows are the incident vectors of the subsets. Okay, and I say that the clutter is ideal if this set covering polyhedron is integral. Okay, I'm just repeating the same question again and again. And let me give you some examples of ideal clutters. Okay, so if this matrix is totally unimodular, then it's automatically integral. Okay, maybe this is more interesting example. If you collect the ST path of a graph, then that's also ideal. Okay, can you guys guess what are the 0-1 solutions for this polyhedron? You just collect the set of edges intersecting all ST paths. Can you guess? Can you guys tell me what it is? Yeah, they're just ST cuts, right? So ST cut intersect ST paths, every ST path. There are more examples in the combinatorial optimization middle. So if you collect the T-joins of a graph, then that's also ideal. Okay. Also, if you collect the clutter of dijoins of a digraph, that's also ideal.
What are T-joins of a graph?
So a graph consists of a graph and a set of vertices. And T-joins is basically a set of edges. If you look at like symmetric differences of the vertices that appear in the edges, and T is a set of vertices that we made. So odd degree vertices in the edge subset.
The vertices in T
Yeah.
odd degree, but outside.
Yeah. So the T-joins are important in traveling salesman problem. I mean, when your graph has an Eulerian tour, that will give you some cycle containing all vertices. But if it does not, if it has some odd degree vertices, then you can fix the odd degree vertices in your graph, and then to do those things, you need to define what I call T-joins. Okay. The dijoins of a digraph are that, so if you pick a dijoin, and then if you contract the arcs in a dijoin, then the digraph becomes strongly connected. Okay. A dijoin is the one intersecting all die-cut in a digraph. Okay. And if you take the clutter of odd circuits of a weakly bipartite graph, then it's also ideal. Okay. So there are many examples in the literature. Actually, I'm always fascinated by these examples, like these pioneers in the community looked at this question before. Okay. Actually, like these rich classes suggest that it might be hard to characterize when a clutter is ideal. In fact, it's co-NP complete to test whether a clutter is ideal. Okay, which means that the testing integrality of this polyhedron is co-NP complete. Okay. Let me mention that if you switch the directions of this linear system, then the same problem becomes polynomial-time solvable. And the integrality of this system is relevant to what I call perfect graphs. Okay. And the goal of this talk, so even though it's hard to completely understand when a clutter is ideal, the goal of this talk is to better understand when a clutter is ideal, broadly. Okay. To do that, my approach will be that I'm going to understand what are non-ideal to understand what are ideal. Okay.
Is it obvious to write this is co-empty? You may have to find some rational.
Right. So you're
non-integral.
right. You just need to exhibit a non-fractional extreme point, but you just make sure that the encoding size is polynomial. For this one is coming from a graph, so you can easily say that the fractional vertex has some polynomial size encoding size. And
But that's when you try to prove the hardness, right? When you want to say something.
you mean NP hardness? So this is NP hard and this is co-NP. So
It's co-empty, so we.
proving NP hardness is more difficult.
Yeah, that's the easy part.
Oh yeah.
Why it's co-empty?
So when it's non-ideal, you just need to exhibit a polynomial-time certificate. When it's non-ideal, so when it's non-ideal, meaning the answer is no, then there's a poly-time certificate for the no answer. That's what I meant by co-NP.
So there's a guarantee that you.
Yeah,
This
yeah.
type of basis.
I don't remember actually, but my guess is it's coming from graphs, and it's easy to define the fractional vertex if it is. Actually, let me get back to that question later. Okay. So I just defined ideal clutters, and I gave you some examples of ideal clutters. Okay. And I'm gonna give you some classes of non-ideal clutters now. Okay. And this is the first class is coming from combinatorial design. They are called deltas. So basically, you have n points, and n minus 1 point are on the same line, and there's one last point that's not on that line. And then you are drawing a line between that point and each of the other n minus 1 points. Now you collect the lines of this graph. Okay, I have 1, 2, 1, 3, and 2, 3 all the way up to n. And then if you write down its incident matrix, you get this one. Okay, it's easy to see that this clutter is non-ideal because if you look at the corresponding set covering polyhedron, okay, you just need to exhibit a fractional vertex. Okay, so I didn't actually define what a vertex is, but if you imagine the n-dimensional Euclidean space, if you have n linearly independent hyperplanes, that will define a point. Okay, so I say a point is vertex or an extreme point if it's tight at some inequalities. Tight meaning these inequalities become equalities, and then those define hyperplanes, and you can find n linearly independent hyperplanes. So you just need to exhibit. You just need to find inequalities that are tight at this vertex, and you have to find sufficient number of ones. So if you look at these ones, so that corresponds to these linear inequalities. So these are tight at this point. You can easily see that because the summation of these two, so n minus 2 over n minus 1 plus 1 over n minus 1, that's 1. And then the last one is basically summation of this n minus 1 of this. Okay. And the rank of this matrix is n. Okay. So this is non-ideal. And the next class is coming from odd-hold. Okay. So you just collect the edges of this odd cycle. Okay. And because n is odd, its incident matrix is non-singular. And this is non-ideal because 1/2 every point is an extreme point. This point is tied at all these linear inequalities. Okay. I can slightly modify outflows by adding some minimal hyperedges. Okay, as long as on hyperedge is minimal, you can add it to the graph. Okay, but this is still non-ideal because the same 1/2 every point is a fractional version. Because the inequality that I've added have 3 non-zeros, so this point is still valid. This inequality is still valid for this point. It still survives after adding this system. Okay, so extended autos generalize autos, and then they are also ideal, non-ideal. Okay. So far, I gave you some examples of ideal clutters and non-ideal clutters, and then let me move on to some important notions of notions in ideal clutter theory. So the first notion is the notion of minors. So there are graph minors and matrix minors. They are actually relevant to clutter minors. But I'm not going to define the connections, but I'm going to define what the clutter minors are here. Okay. So if you give an ideal clutter, then you know that the set covering polyhedron is integral. And there are 2 operations that preserve integrality. One is to take a face of that polyhedron. So by taking a face, I mean you just collect the subset of extreme points. Because all vertices, all extreme points are integral, even after taking a subset, it's also integral. So every face is also integral. Okay. Another operation is the operation of taking projections. So you just kind of they are sometimes called orthogonal projections to the low dimensional. And then if you look at the polyhedron in the projection, their extreme points are coming from extreme points in the higher polyhedron. And then that's why they are integral. Okay. Using these 2 observations, you can define minors that are set theoretic. You just pick an element U, and the first operation contraction is the following. So you just take out this element U from every subset, but maybe some of the subsets become non-linear, elimination. Now you just collect the minimal ones. Okay. That's the same as setting the corresponding variable to 0, which is equivalent to taking a face. Okay. And deletion is basically that you just eliminate the members containing this element U. Okay. You're just eliminating the inequalities. But that's the same as setting projecting out this variable xu. Okay. But you don't have to remember what they are for this talk. But the main takeaway is that these 2 minor operations preserve idealness or integrality. Okay. So clutter is ideal, then all its minors are ideal. Which means that if you find some minor that's non-ideal, it means that the original clutter is non-ideal. Okay. So I was interested in the question of testing idealness of a clutter. So before we test whether a clutter is ideal, maybe the first thing we can try is whether this clutter contains one of these as a minor. Because I know that deltas and extended autos are non-ideal. If you find one of these as a minor, that automatically implies that this clutter is non-ideal. So the first question is, can you test whether you have this as a minor? Okay. But actually, this empirical result was coming from the recognition of these as a minor. So this will answer your question from here, right? So if you have one of these as a minor, and that always has size n-most n, So the input for the problem is the number of columns is the number of vertices, and the rows are edges.
This liquid is given as a matrix, or is it
As a matrix, as a graph. So, and then you construct the clutter as an incident matrix of this graph. Okay. So this is the reason why actually these two minors are sort of like bottlenecks for understanding idealness. Okay.
Well, so are you saying that this problem of finding a delta or extended alcohol minor is complete? I mean, you're not saying the clutter contains delta and empty contains
So
some issue.
actually it's just I broke this chart. The delta 3, if you look at it, this is a matrix of 1, 2, 1, 3, and 2, 3. This is just a triangle. And extended autors of size n is 5, they're just like odd cycles. So finding delta as a minor can be done in polynomial time. But in this statement, I just kind of made an artificial statement. But for this hardness result, you just exhibit, you just find triangles and odd cycles. But in some sense, I'm gonna show you. Yeah, so finding deltas can be done in polynomial time. But if it doesn't contain a delta, but it doesn't mean anything. Sometimes it doesn't mean anything. It might contain some odd cycles of length n is 5. Or even if it contains a delta, then it's fine. But if it doesn't contain a delta, you still need to look at this odd hole. But that's hard. Okay. But for this statement, just finding odd cycles is hard for this clutter. That's the statement. Any other questions? So this is in some sense disappointing. But we want to look at other classes of minors that are the blockers of deltas and extended autors. Okay, and why are these important? Because the blockers is the second important notion in ideal clutter theory. That's the reason. Okay, and then we're going to ask the same question for these clutters. But the short answer is yes. Okay, so let me define the blockers. Let me remind you the definition of a cover. So a subset is a cover if it intersects every member. It's sometimes called heating set. Okay, and then you can also define minimality of a cover in terms of inclusion. Okay, so the blocker is basically the collection of the minimal covers of this clutter. Okay. The blocker of ST paths is actually minimal ST cuts, not just ST paths. Okay. Okay. There are important properties. One is that if you take the blocker of the blocker, then you get the original one. Okay. And this might be more relevant for this talk. So this operation of taking blockers preserves idealness. Okay. Which means that I told you that deltas and extended autos are non-ideal. So even after taking their blockers, they're also non-ideal. Okay. But the blocker of a delta is actually itself. So we just need to show that the minimal covers of a delta form the same set. So if your cover contains 1, then it's enough to collect one of these n-1 points. Let's say if you collect 1 and 2, then it will intersect all lines, right? But if you don't pick 1, then you have to pick all the points of the line. That's the argument. Okay. Now, just take an auto without hyperedges. Then the blocker of that auto is just a set of the minimal vertex covers of this graph. So in this 5-cycle example, we have 5 minimal covers. But for extended autos, because of its hyperedges, it might be hard to analyze how the picture looks like exactly. But one thing one can say is that every cover has cardinality and is n+1/2. Because you have to cover the edges in list. Okay. To cover and you have, because n is odd, if you start from 1, then 1, 3, 5, and you have to end with n because n is odd. So that picks strictly greater than half the vertices. Okay. So this is all we need to analyze something. Okay. This is the main takeaway for the blocker of an extended auto. Okay. So we proved that finding one of these as a minor can be done in polynomial time. A polynomial in the size of the clutter and the size of the element. So if you get an incident matrix, then this algorithm is polynomial time in the size of this matrix. Okay. So this is kind of like the opposite result from the earlier result. So for the rest of this talk, I'd like to give you some ideas of how to prove this theorem. So we need 2 concepts. One is the notion of dense clutters, and the other is some restrictions as minors. Okay. Okay. So we say that a clutter is dense if it satisfies the following 2 conditions. So the first one is that every cover has size n=2. This one is not an artificial condition because if you have a cover of size 1, it means that there's an element contained in all members. Which means that if you look at the incident matrix, there's a column of all ones. Now you can simply ignore this column by contracting it. So you can assume that every cover has cardinality in these 2 easily. And the second condition is more interesting. So a clutter is dense if there exists a weight vector W, so that this 1 transpose W is the total list, and every member has weight strictly larger than the total vector. This is some sort of like density. So if you assume that W's are all ones, then it's just that the cardinality of every member is strictly larger than n+1/2. Strictly larger than n/2. That's kind of like the extended autos, blocker of extended autos. Actually, if you give me a clutter, you can test whether a clutter is dense in polynomial time by solving this linear program. So basically, if the optimal solution or optimum value of this P is greater than 1/2, then the X will be the certificate weight. Okay. So the blockers of extended autols are dense. Remember that every minimal cover of an extended autol has cardinality at least n plus 1 over 2. So if you plug in O1's vector for W, then it'll prove that it's dense. And deltas are also dense by setting W to this one. Okay. I've shown that the blockers of extended autols and deltas are non-ideal. But you can actually prove that dense clutters are non-ideal. Okay. By something called the width-length inequality by Lehman. Because this is kind of important in the clutter theory, let me just write that down here. Okay. So this is the theorem due to Lehman, 79. So let C be a clutter over ground set V. Okay. C is ideal if and only if there's a non-negative width and non-negative length. So for all non-negative width and length, the product of the following two, so width, minimum width of a member times the minimum length of a cover, the blocker of C, is less than or equal to W transpose M. Okay, so this is the minimum width of a member, and this is sometimes referred to as minimum length of a cover. Okay, so the product of these two must be less than or equal to the kind of like the capacity. Okay, so but by using this theorem, you can prove that dense clutters are non-ideal. Can you guys tell me why that's the case? So you can use the same weight coming from density and just the problem of setting proper length. You can actually set L to O1's vector. So basically minimum width greater than W transpose O1's divided by 2, and minimum length will be the cardinality of a cover. And I assume that the minimum cardinality of a cover is at least 2, because that's what I assumed initially to define density. So this is at least 2, right? So if you take the product of these two, that's greater than W transpose 1. So that's violating this inequality. Okay. So if you define dense clutters, I know that they are non-ideal. But I can actually prove more. Every dense clutter has one of these as a minor. Okay? And remember that all minors of an ideal clutter are ideal. So if you have a non-ideal minor, then that will mean that the original clutter is non-ideal. So because I know that a delta and the blocker of an extended autol are are non-ideal, dense clutters are also non-ideal. I also gave you minor characterizations for that thing. Okay. Any question? Great. So this will imply the following corollary. So I wanted to find the delta or the block wall of an extended auto as a minor, but that's the same as finding a dense clutter as a minor. Let's just forget about restriction for now, right? Because a dense clutter contains a delta or the block wall of an extended auto, and then these themselves are dense. Okay. So what is a restriction minor? It's basically so if you pick a subset of the element set, by restricting I mean you just delete these elements I, and constructions only follow only when you have some covers of size 1. So basically, if you have this matrix system, if you delete this element, then you need to delete the rows here. Now then this element will appear in every row. You just need to contract this. The contraction only follows when there's a cover of size 1. Okay. So the thing is, so to find the delta or the block curl of an extended auto, you just need to look at all restrictions and then see when they are dense or not. And I told you that testing whether a clutter is dense can be done in polynomial time by solving an LP. But the thing is, there are exponential number of restrictions, because for each element you can either to keep it or delete it, and contractions just follow them. But the thing is, if you have a dense clutter as a restriction minor, then there are always this small certificate. Basically, you can find 3 rows that will guarantee that there's a dense restriction. Okay. So this will give us a polynomial time algorithm. Okay. So so these are our main result. So one is to kind of like some structural result for a dense clutter, and the next one is the algorithm for finding it. Okay. Any question? Okay, I have.
How bad is the run?
You just need to collect. You just look at any triple of 3 members. So if the number of members is n, you just need to go through m cubic time. And then taking restrictions and finding delta. I mean, if you give me a clutter, you just need to run an LP to check density. Then the complexity of LP algorithm also is appended for these m cubic triples. But that's basically it. Oh. So if you don't have any questions, I have like 15 minutes, so I want to kind of give you kind of intuition of how to find these as a minor. Okay. Okay. So they depend on, they use 3 tools. So one is the following. So if your clutter has the following 3 rows, then you can guarantee that there's a delta as a delta minor. So this is basically two rows have a common element V, okay, and then their union, except this element, is contained in another row C. Okay. If you forget about these columns, they sort of look like delta 1, 2, 1, 3, and 2, 3, or something like this. So if you have this configuration, you can always find the delta as a minor. But this is one tool. The next one is now you look at a clutter, and there are the minimum size of a member is 2. Now you look at the collection of size 2 members. Okay, then they correspond to graph. Okay, the columns are labeled by vertices, and then those members correspond to edges. Okay. If that graph is non-bipartite, then you can find an odd hole. Okay. Now you can delete the other vertices. You get an extended odd hole. In this example, you have this 2k plus 2 element. If you delete this element, you just keep just these extended odd hole. You could have other hyperedges also. Okay. Now you look at a graph, you can look at a clutter, and whose minimum cardinality members have size 2, and that corresponds to some graph. If that's non-bipartite, you can find an extended odd hole as a minor. Okay. So you can assume that that graph is bipartite. Okay. But this lemma shows you more. Okay. I know that the graph should form a bipartite graph. Now I can say something about hyperedges too. Okay. If there's a hyperedge which is monochromatic, then you can find a delta or an extended odd hole as a minor. So the idea is, even though it's a hyperedge, but if you add an edge to a bipartite graph, then you can find a loss cipher. Now you are just adding a monochromatic edge, which have cardinality greater than 2. But you can find a delta or an extended odd hole as a minor. Okay, that's an intuition. But this graph must be connected, by the way. Okay. Do you know, can you guys guess how I can use these two tools? I mean, if you give me a clutter, then which is dense, then it's kind of not the case when it doesn't necessarily have cardinality 2. How do I use this? Basically, if you give me a dense clutter, you move to the blocker, and then I assume that the blocker has minimum cardinality 2. Now, if in the blocker, you can find a delta or an extended odd hole minor. Then if you move back to the original clutter, you get the blockers of these as a minor. So I'm going to apply these two tools in the blocker. And then I can find these as a minor. And then I get the blockers in the clutter. Okay. So remember that a clutter is dense if it has every cover has cardinality n is 2, and there exists a way to certify that. Okay. If you move to the blocker, then every member of the blocker has cardinality n is 2, and this weight is satisfied. Okay, again, I move to the blocker and then find the delta or an extended odd hole by using our tools, and then I just move back to the original clutter. Okay. In fact, you can assume that the minimum cardinality of a cover is precisely 2. That can be done by deleting some columns and constructing some columns without losing the desired property, without losing the density of the clutter. Okay. And then I can, and because the minimum cardinality of a cover is 2, I can collect the cardinality 2 covers, and I can draw the graph. And by using the second tool, I can say that the graph is bipartite. Okay, but it's not necessarily that the graph is connected, but I can assume that the graph is connected for now. You can treat like other components separately, but I'm not gonna cover that argument. But let's just assume that the graph is connected. Okay. So this is the last slide, by the way. So now I can assume, I have a connected bipartite graph, okay? And because I assume that the clutter is dense, I'm gonna create a monochromatic cover. The cover contained in one of these two sets. Okay? Let's just assume that the weight of B is, and this the weight of R. Okay? And you know, I want to say that B is a cover, which means that if I exhibit a member, they must intersect this set B. Okay. So let's suppose not. So which means that there's let's suppose that there's a member completely contained in R. Okay. Then the weight of that member is less than or equal to the total weight sum of the elements in R, because that member is contained in R, right? But I know that the weight of R is less than or equal to the weight of B. So the weight of C is less than or equal to the half of the total weight sum. But that's a contradiction, because I assume that my clutter is dense, the weight of the C must be strictly greater than the weight of the total weight sum. Okay, that just shows that no member is completely contained in this set R. So if you give me any member, they must have an element in this set B. That means that B is a cover. And because B is a cover, there's a minimal cover contained in B. So there's a monochromatic member in this clutter. So by using the last tool, you can find the delta or an extended outward as a minor in the cover, in the blocker. Now you can move to the clutter and find the blocker of a delta, which is delta, or the blocker of an extended outward as a minor. Okay, so I think this is it.